Again, looking at the graph here, we want to know when does the derivative not exist. So looking at each of those, where might the derivative of the function not exist? So can you list out all the x values where there is no derivative, where it's not differentiable? Okay, let's go with Kiani. Give me one place we don't have a derivative. At 1? Yeah. Why? What's our reason? We have that jump discontinuity, right? Okay. Kelvin, give me another one. Okay. So at 2 we have, let me actually write those down. So this is going to be a jump because of the jump. At 2 because of that vertical asymptote. Okay. Let's see. Lydia, give me another one. Yes. So so there's actually kind of two reasons there, right? We have the removable discontinuity, it's not continuous, and we have a sharp turn, right? So both of those definitely could, so we can say a hole and that sharp turn. Okay. Okay, any others? Matthew? 0, and our reason? Sharp turn. Is that all you guys came up with? I have 2 more. Yeah. The endpoints as well. Because are we continuously going through those? No, right? So those, thinking back to the homework problem, you can kind of set up maybe a one-sided derivative, but do we ever talk about one-sided derivatives? Not really, right? The only way we could really address that is if we're looking at the limit definition, and we don't do that very often. So the derivative as a whole would not exist there either. Okay, so I would also include -4 and 5. Okay, so key questions to ask yourself is, one, is the function continuous at each point? So is there any place that it's not continuous? When we saw those, we had a jump, we had a vertical asymptote, and we had a hole. Is there a tangent line at every point? Okay, that'd be a good thing to know. And does the derivative from the left equal the derivative from the right? So the derivative from the left and the derivative of the right really come into play at something like the sharp turns. If I was to zoom in on this one, if I was to do the derivative from the right, well, that'd be equal to the slope of that line, right? I could say, hey, there's a tangent line there. That's tangent. But then I could also look at the derivative from the left and say, hey, from the left, this looks like what my derivative might be. And are those two lines equal? No, right? The derivative from the left is not equal to the derivative of the right. Even though we're continuous, that does not happen. That is no good, okay? So this is especially important if you're given a piecewise function to look at, and you're just given the piecewise function, you're not given the graph, so you don't know if there's a sharp turn or not. I can create, and I can create piecewise functions that go from a quadratic to a linear function, and yet it's differentiable. And that's because the derivative from the left equals the derivative from the right. They match up. Do you want to see one of those created? So if I was to go into Desmos, so quadratics and linears are very easy, because if I was to, let's say, let's go with this. Let's see. Desmos. Okay, so if I was to do a quadratic, let's just say something very easy. Y equals x squared. What is the derivative at 1? So let's actually make this to be, no, not up there, down. Let's cut this off at 1. So let's say this is less than or equal to 1. Okay? What is the derivative of that quadratic at 1? What's the derivative of x squared? 2x. Plug in 1. 2. So, and we can even actually say that. Let's call this f of x. And so f prime at 1 is 2. Right? So what I need is I need a linear function with a slope of 2. Right? So I could say g of x is equal to 2x. But now I need it to just make sure it goes through that same point. So what would be a y-intercept that would also go through that same point? -1, so -1. And then I cut it off, I say that's going to be for x is greater than 1. That's differentiable. Even though it's a piecewise function, is there a sharp turn at 1? No. It looks almost like it's supposed to go straight through there. But that's because the slope of the line and the derivative of the quadratic both equal the same thing at 1. I can do that. G prime at 1. Oh, that's because let me put equal to there. There we go. They're both the same. Okay? So even though I have a piecewise function, I'm cutting out the quadratic and going with the linear, but because the limit from both, the derivative from both sides is equal, they match up perfectly and they go from the quadratic very smoothly into that linear function. And there's no sharp turn. Does that make sense? So that's when we're talking about the derivative from the left and the derivative from the right need a match. It can still match even though they're two different functions. You just have to make sure the derivative from both sides is the same. One, they have the same value. One, you need to make sure it's continuous. But then that the derivative is matching on both sides. Because if I was to change this to maybe a slope of 3 or something, obviously I would have to bring this down maybe here. Now are the two slopes matching? The two derivatives? No. Do I have a sharp turn now? Yes. So that one is now not differentiable. Okay? So, let's see. So if the function is continuous and a tangent line exists at a point, then do you think the derivative exists at that point? Well, not necessarily. Okay? So, differentiability and continuity. So if a function is differentiable at a point, the function must be continuous. So that is always true. If you remember from last year, we said if it tells us the function is differentiable, we can automatically assume that that function is continuous. However, we cannot reverse that. We cannot say that if a function is continuous, then it's differentiable. And here are 3 examples. So the second 2 are our sharp turns. The first one is not a sharp turn. It's nice and smooth, but the derivative at 0 still does not exist. Do you know what the derivative at 0 of this first one is? Yeah.
Undefined because it's a vertical line.
It's a vertical tangent line, so therefore it is undefined. Yeah. Okay? So anytime we have a vertical tangent line or an undefined derivative, it could still be continuous, but it's not differentiable there. Okay? So anytime we have a vertical tangent line or we have a sharp turn are places where we could be continuous, but not necessarily differentiable. Okay? However, the reverse is true. If it's differentiable, then it must be continuous. That we can guarantee. And so that is a very, very good one because they'll throw that at you on an FRQ. Instead of saying it's continuous, they'll say, hey, this is differentiable. But you have to do something about that requires continuity. And so you have to then be able to say, hey, because it's differentiable, it's continuous and be able to use that. Okay? All right, let's look at problem number 1. Which of the following statements, if true, cannot be used to conclude that f of 0 exists? So go through those and determine which one, if true, cannot be used to conclude that f of 0 exists. Okay, let's bring it together as a class. Let's see. Ethan, what do you think? A, B, C, or D? Why? Very good. There could be a hole, right? A removable discontinuity. So just because the limit exists does not mean the value exists. Whereas all the other ones, do they guarantee a value? Yeah, if it's continuous, is there a value? If it's differentiable, is there a value? Yes, because if it's differentiable, it's continuous, and thus there's a value. If there's a y-intercept, is there a value? Yeah. Just because there's a y-intercept does not mean that there's necessarily there's continuity, but that's not what they're asking. They're asking about a value, right? All right, good. Look at problem number 2. So we have the figure above shows the graph of the function f, which has a vertical tangent line at 4, and a horizontal tangent line at 5, which of the following statements is false. So what do you guys say? C, why C? It's not differentiable at 5. It's not C. It's not differentiable at 5 because there's a horizontal tangent line. Oh, it's asking for it as false. Oh, okay. I wasn't paying attention to that. So good job, guys, for paying attention. So f is not differentiable at 2. That's true. Not differentiable at 4. That's true. Differentiable at 7. Okay, very good. All right, let's go on. Okay, basic differentiation rules. So these are our basic ones. We should know these. Okay. X to the n. What's the derivative of x to the n? To the what? N minus 1. Good. What's the derivative of c? Okay, what happens when I take the derivative of two functions being added? Yeah, so f prime plus or minus g prime, right? Okay, what's the derivative of c, a constant times a function? So this is like, I don't know. What was that? Just c times f prime. Good. C times f prime. That's all, right? So that'd be like if I had like 2 times, and then, I don't know, we put something in there, 3x squared. Well, that would just be 2 times what? 6x, right? If I was to take the derivative. Which would then be, yeah, 12, right? Okay. Go ahead and look at problem number 3. Okay, do we need to discuss it?
Yes.
Okay. You see what I wrote up there? So that's our definition of a derivative, right? The limit of, as h goes to 0, of f of x plus h minus f of x over h is f prime of x. So then the question is, what is f of x? Any thoughts? Not 2. So here, let's point something out. Look at this part I'm putting the arrow at. Is that saying exactly x plus h? Does it? What does it say? Right here. Does that exactly match what I have? No. Instead of x, what do they have? So they've plugged in x equals 8. So this is the derivative of f of x at 8. Not at 8. Yeah, at 8. So therefore the 2 is, so this is actually the limit of h going to 0 of f of 2 plus h minus f of 2 over h. and that's going to be equal to f prime of 2. So the 2, now, oh, dang it, I made a mistake. That's, I keep on wanting to do the 2. That's 8 plus h, sorry, f of 8. And that should be f prime of 8, sorry, I want the 8 instead of the 2. Okay, but regardless, that minus 2 is f of 8. So what is our function? Look at what we have here. What's our function? X to the 1/3. Which is what you had, actually. You just then had a minus 2 afterwards. All right, if you take off the minus 2, then you had it. Okay? So x to the 1/3, or the cube root of x. All right? And then if we think about it, f of 8, well, what's the cube root of 8? 2, which is what we have there. So it all matches. So now we need to figure out what is f prime of 8. But first, before we can do that, we need to know what f prime of x is. So how do we do that, guys? Power rule? So what do we do?
Check the put the 1/3 in the front and then subtract 1/3 by 1 for the exponent, so you get 1/3 times x to the negative 2/3.
1/3 x to the negative 2/3. So that would be 1 over 3 times the cube root of x squared. All right. So we're getting closer. So f prime of 8 then, 1 over 3 times the cube root of 8 squared. What's 8 squared? Without a calculator, we can do this. What's the cube root of 64? Four. So 1 over 3 times 4 is 1/12. B. Another way to do that power is this. I actually like to do, if I was to do 8 to the 2/3, you can do the way we did it, the cube root of 8 squared. You could also do the cube root of 8 squared. What is the cube root of 8? And then 2 squared is 4. Either way, we get 4. Right? You can do the cube root of 8 and then square that, or you can square the 8 as we did over there and then take the cube root. Doesn't matter. Okay? Any questions on problem 3? Good there? Somewhat good? Maybe good? Any clarification needed? Okay. Try problem 4. All right, guys. Do we have a limit for, or not a limit, a derivative of 3? Derivative does not exist. So, things you would want to do. First, check continuity. Okay, which I think is what you guys did. You checked continuity, right? So the limit, so let's say check continuity. And this would be important to do, Matthew. Okay? So check continuity, because first off, if this isn't even continuous, do we need to worry about a derivative?
No.
No, so it's important to check continuity first. So we would say the limit as x goes to 3 from the left of g, is that equal to the value, and is that equal to the limit from the right? Okay? So what do we have? That'd be 3 minus 3. That'd be, what, 12 minus 3? 12 minus 12 and 12 minus 12. What do we have there? 0, 0, and 0. So is it continuous? Yes. So, yes, continuous. So now what do we have to check? Is it differentiable? So then we have to take the derivative of both of those. So then it might be useful up here to say, well, what is g prime of x? What's the derivative of 3 minus x?
0.
Nope. Negative 1. For x is less than 3. What's the derivative of 4x minus 12? 4. For x is greater than or equal to 3. So now we are going to check continuity. So how can we set this up to check continuity? Well, what's the idea? The derivative from the left has to equal the derivative from the right. And we can write it in this way. The limit as x goes to 3 from the left of g prime, is that equal to the limit as x goes to 3 from the right of g prime? Well, what is the limit of g prime from the left? Or what is the derivative from the left? What was it? Negative 1. What was the derivative from the right? 4. Are they equal? No. So not, or there is, so let's see, g prime of 3 does not exist. It is not differentiable. Not differentiable. Okay? Does that make sense?
Yeah.
You always want to check continuity first when you have a piecewise function, because if it's not continuous, it's not differentiable, and you can just stop there. But if it is differentiable, or sorry, if it is continuous, then you want to move on and check differentiability. Oh, I put check continuity twice. Sorry. Fix that. That should be check differentiability. Okay? Any questions? All right. Okay, do problem 5 and 6. Actually, 5, 6, 7. Do the last 3 problems. All right, let's just check in with number 5. Did we get negative 8 for number 5? Awesome. That's what I got. So just take the derivative of each, plug in the values that they gave us. We're good. All right, so it should be on to number 6. Okay, do we have an answer for number 6? I got 14. You guys getting 14? Okay, good. All right, on to number 7. How did we do on number 7? I got negative 1/2. All right, awesome.